Hello, everyone. Let's give it a couple of more minutes for some of other friends also to join us as people are dropping in. We will start shortly. Perfect. I think we can start our webinar today. Hello, everyone. Good morning, good afternoon, good day, wherever you're joining us from. My name is Mona Amriasari, and I'm working as an application specialist with Technobees. I will be your host today, and it's my pleasure to welcome everyone to the webinar today. Okay, let's start first. Perfect. So this webinar is on accelerating polymer solubility screening from experimental design to the co-solvent system optimization. This webinar is being recorded and will be available to you all in the next coming days. The webinar will take 30 to 45 minutes, and I'm happy to answer any questions after we are done. Please put your questions in the Q&A section. If I didn't get time today to answer your questions, I will be happy to be in touch with you through emails. If you have any questions after this webinar, please feel free to email it to us at info@crystallization-systems.com, or you can send it directly to me at mona.amriasari@technobees.com. But before I start, let's talk a little bit about the Technobees. Technobees crystallization system is a Dutch company located in north of the Netherlands. We are the world-leading technology provider for solid-state research, process development, and formulation. Since 2005, our platform for accelerating material research or pharmaceutical research started with Crystal 16, and then Crystal Breather and Crystalline has been added, which we have a global presence in all the crystallization systems products. But since 2024, we started a new portfolio on process chemistry, introducing the Reactol for all the process chemists in many different fields that they want to optimize their process, have a better understanding of their reactions, and do the kinetic modeling. Since 2025, we also introduced the Dosal as a liquid dispensing module for reagent addition to the reactions. Reactol has 5 parallel reactors with auto-sampling technique, which is where the magic happens. We also have quench and dilute, rinse, and waste bottles on the top of this medium throughput screening system, which after the sample has been taken, it will be immediately quenched and dilute and send it to these HPLC trays for further analysis. It is designed to address the needs of chemical reaction screening, from route scouting to reaction screening, effects of the solvent, reagent, catalyst condition, to the reaction optimization, and also kinetic profiling and modeling. So that is about the Reactol, which fills the gap between the medium high throughput experimentation or larger volume of the material. But we also have the crystallization products in line. Some of you might already know some of these or worked with both of them or one of them in your lab, especially Crystal 16 and Crystalline. Today, we will talk about the Crystal 16 and how we use these techniques in more material science approach. but crystal 16 has been out for solubility and metastable zone width screening, for solid state screening, and has different field of study. Use crystal 16 from pharmaceutical to agrochemical to bio and many different applications. Second would be crystalline, which is equipment for optimizing your reaction, optimizing your crystallization process from habit control, particle size, and it has cameras and can be equipped with Raman for more in pseudo measurements. The cameras act as a microscope for your system. We also have crystal breather, which has the vapor diffusion technique, which is designed for single crystal growth. With all the perks that crystal breather offers, or the gadgets that it offers, from vapor diffusion to controlled evaporation, you can make your single crystals in the NMR tube and use that for more small volume. Technobeast manufactures lab instruments, which enables you to measure, characterize, and control some of the parameters, properties related to crystallization and during this webinar today. So again, if you joined us right now, welcome everybody. My name is Mara Amrehesari, and I will be presenting today a part of my research during the PhD and postdoc on accelerating polymer solubility screening and how we built from these two optimizing a system for the DOE design for the co-solvent system. This research has been done at Georgia Tech, so some of my slides have the Georgia Tech name on them, so welcome. I would like to start with this slide because I think the greener future is a must. This list shows the sustainable goals set by United Nations for 2030. As a responsible citizens and as a profession, in our profession as a chemical engineer, chemist, wherever field that we are coming from, responsible consumption as production is one of the things that we can contribute definitely. And I think we can contribute mostly in that perspective in our profession. And why do I sharing this and how this research will fill kind of this gap or contribute to this is that because in this research, we are accelerating polymer solubility screening for more sustainable process development. And I can at least think of 4 ways that this research can contribute to the greener future. The first is that with having the knowledge from this research, we can swapping the dangerous or unsustainable solvents with more green solvents. We can replace some of the solvents that are commercially banned from some countries and find a better or greener solvents for the processes. And also decrease the solvent usage by knowing exactly what is the solubility profile of the system, and under the temperature or concentration. Knowing this knowledge, we can precisely design a process that requires the minimum solvent. We also can develop a new dissolution and precipitation processes or application, or design some materials with specific characteristics, or reverse engineering some of the materials by knowing that what would be the characteristics that it is required. And why should we care about the polymer solutions in general? Polymers are based in many applications. This is the material class that draw a lot of attention in the recent years. And it can be based on many applications, from paints and coating to polymer membranes, from the formulation or having the cosmetics, and in drug delivery as excipient or the carrier of the drugs. Also, plastics recycling is one of the areas that the solvent usage or having this knowledge on dissolution and precipitation can contribute to the less solvent usage in the industrial processes. So knowing what is the solubility of the polymer solution can help us with process design, having a suitable solvent for application, also with polymer design with the specific solubility characteristics. So how can polymer solubility screening be accelerated? This is the topic of the webinar, how we can do this process. Now that we know that these are important, it's important to know what is the solubility look like. In this webinar, I'm trying to answer two questions. How do we generate a reliable polymer solubility screening process? What is a comprehensive data set look like for this specific field? And how we can improve from there, how we can go from the knowledge on the binary polymer solvent system to guide the co-solvent screening. So the first question is that how we can generate a reliable polymer solubility screening process. Or what is the comprehensive data set anyway? Why this is important? I just want to pause here. I'm sure some of us Googled what is the solubility of one polymer in this, or we were wondering how we can find the right solvent. If you do a Google search, you will hear either it's soluble or insoluble. There is not a lot of data or information out there that help you to guide your design. You do a lot of try and error, but still you cannot find the right solvent for your system. That is because there is no comprehensive data set out there that captures all the factors that impact the measure solubility. A comprehensive data set should include all the key factors that it's influencing the target property. In polymer solubility specifically, that can be a temperature, concentration, molar mass, and measurement parameters. And if we Google search, there is, in a rare case, we see some of this information, or even we can get the information on what instrument has been used to capture this data. So this means that there is no backstory behind the data points, behind the soluble or insoluble. And why is this important? Why I'm sharing that? And what did we do to address this problem? We developed a standardized method and built a data set for the polymer solution. How we did that, let me just walk you through some of the steps and the instrumentation. We used Crystal 16. This image is different from the slides that I previously showed you because all this research has been done in Crystal 16 version 2, which uses the turbidity measurement system, basically. For that, we have 1 milliliter of the solvent. When the solution is clear and all the polymer is dissolved in the solvent, you get 100% transmissivity. As the polymer starts precipitating out of the solution or phase separation is happening, then transmissivity drops to a lower value, which is captured by the system. This is a typical result of the Crystal 16 shown here. This experiment has been done in 2 cycles of heating and cooling, shown with the red dashed line, and at 4 different concentrations. The black line shows the 5 milligram per milliliter of polypropylene and toluene, and the gray would be 50 milligram per milliliter. So as you can see, the Crystal 16 can help us to monitor what would be the phase change during the change in the temperature in a thermal method. So we introduced some cutoffs to this system and said, okay, if anything is above, if the transmissivity, which is outcome of the Crystal 16, is above 85% for a solution, 200, let's categorize that as a soluble material. If it's below 10%, let's have that as insoluble. And between 10 to 85, let's classify that as a partially soluble, because the soluble does not go to the fully or clean state because the transmissivity dropped to a lower value a little bit, but it's clear for most part. There are still some precipitate floating in the wire. Let me start with the challenge. Why this method is valuable? Why did we choose this method? Polymers are large molecules. They are moving very slowly. Their dissolution behavior sometimes takes from days to months to be dissolved. And both kinetics and thermodynamics are important for phase separation. But the changing in environmental conditions, like temperature, can change the quality of the solvents going from good to bad. or from the theta solvents when all the attractive and repulsive forces are in equilibrium with each other. So the polymer is in most relaxed form, and changing from theta condition to good and then to poor, where the phase separation is happening. And the polymers start forming from the coil to the globule state. So crystal 16 would provide us with this polythermal method to precisely control the temperature and also adjust the heating cooling ramp rate, because we are dealing with a very large molecule, to screen the changes in polymer condition, polymer solution condition, as we are changing its environmental condition. But this task for standardizing a method was specifically challenging because we are not dealing with the same material that has the same solubility profile. This is an example of polyethylene glycol in ethyl lactate over different concentration. Again, the black line is 5 milligram per milliliter and goes to 50 milligram per milliliter for the gray color. And this polymer specifically has upper critical solution temperature, meaning that if you are going to the higher temperature, polymers start dissolving fully in the solution and become one phase. And as we're changing the temperature to bring it down to a lower temperature here at 10 degrees C, the polymers start precipitating and phase separation is happening. But is this the only behavior that we see in the polymer solution? No, we have also the polymer like polypropylene in 3-methylpyridine example that has the LCSD behavior, meaning that the polymers start getting dissolved, the transmissivity goes up at the lower temperature, and at higher temperature, the transmissivity drops to a lower value. But this is not the end of the story. Some of these polymers have both UCSD and LCSD behavior in the same solvent, which makes it very challenging to find out or standardizing a method that we can capture all these changes in the polymer solution. Just looking at these two examples, you will see that these polymers start going back to the 100% transmissivity for all concentration, despite how the concentration is going up. At higher temperature, while this example is not reaching to the 100%, but progressing in this solution. So these differences between the system makes it very fun and interesting to navigate and find a standardized method that we can measure the solubility of the polymer. So to design our process, this shows the fishbone diagram for looking at what is the final properties of interest and what are some of the parameters that are affecting this phenomenon. So we are here looking at the measured solubility of a polymer. And we have materials as solvent and polymers, and different characteristics of solvent and polymers here are shown that is affecting the solubility of polymer based on the literature or what we know. And we also have the measurement parameters, because we didn't know at the time that how crystal 16, or how we can collect the data in a way that it's meaningful across different behavior of the polymer solutions. So for the next couple of minutes, I will be more focused on the measurement parameters. We did not do anything on the material side, except the fact that we kept the molar mass to a lower value to avoid a lot of kinetic complication. We selected anything that we could commercially bought below 15K on the molar mass, and we only focused on the measurement parameters for standardizing our method to looking at more high throughput data collection. So this slide shows the experimental design space that we were looking. We have heating ramp rates and cooling ramp rates. We keep both of them the same because changing one versus the other might change the solubility behavior of the polymer and the metastable zone widths that we were looking at. The number of cycles is another parameters that we look at. Either we just keep it at 1 cycle or 2 cycles for faster data collection. We looked at its wide range of mixing rates from 300, I think 200 to 900 RPM, and different hold time, basically, combination from 15 minutes for hot and cold, which is very norm with pharma studies, to maximum at 60 minutes at hot temperature and 2 hours at cold temperature. We also looked at different concentrations of the material. So looking at all these variables and try to standardizing our method, I will cover some of the findings that how ended up with the standardized method that we went with. For this study, we looked at the transmission percent during the isothermal hold. So this is the example of polyethylene glycol in toluene. So we picked two polymers at the same solvent. One has a UCC behavior and the other has the LCC behavior, which I'll show in the next slide. Here on the right, you will see the plot of the transmissivity versus the cooling ramp rate as these polymers start precipitating at lower temperature. What we observe is that we get to a plateau value at 1 degree C per minute, but before that, the transmissivity is higher when we have lower cooling ramp rate, meaning that the size of the particle is not big enough, or the drop is not fully comes down to the transmissivity change to a lower value. But we are looking at the, if it's statistically significant, there is not a significant between moving between different cooling ramp rates. And then we looked at the polypropylene toluene, which has the LCST behavior. On the right side, again, you will see the transmissivity versus heating ramp rate as these polymers start precipitating. And we looked at this hot and cold during the precipitation because we believe that this cooling and heating ramp rate can affect the size of the particle as the precipitation is happening. Higher heating ramp rate here led to a smaller precipitate and higher transmissivity in comparison with the lower heating ramp rates. The 50 milligram per milliliter shows that the same trend as we have on the top, but it falls within the insoluble region. So again, we are working with large molecules. So far we compared two systems of LCST and UCST behavior when we observed the change of the transmissivity on the particle size. And we concluded that there is an impact on the particle size forming during the precipitation. So the change in the particle size also leads to the change in transmissivity. But since the change was not very statistically significant, we went with 0.5 degrees C per minute to not have very long experiments compared to 0.1, but also be able to give the polymer enough time to catch up with some of the changes. And I will show in the few slides that why this is very important for large molecules. Next, we looked at another parameter, which is mixing speed, which has little impact on the transmissivity plateau value on the system as the system reaches to the equilibrium. These are, again, the same model polymer system, polypropylene toluene and polyethylene glycol in toluene. And we see for 5 milligram per milliliter and 50 milligram per milliliter, the transmissivity is very consistent and there is no statistically significant changes. So we concluded that this equilibrium transmission is independent of the steering speed. Since we are dealing with the large molecules, we kept it as higher mixing speed to facilitate the agitation of the polymer and avoid the gelation and other complications that might happen as the dissolution is happening. For assessing the high throughput, if there is a possibility to collect the data for high throughput data collection, we needed to analyze if the data during the ramp is matching the data during the isothermal hold. So on the left, you will see the polypropylene in toluene transmission percent versus the temperature. What we can conclude from comparing these two systems is that the system on the left has very fast kinetic, gradually changing with the temperature. So transmissivity is catching up with the changes in temperature as the polymer solution is going from one phase to the other. Versus on the right, for polyethylene glycol, we see a little bit of sharp drop, meaning that the kinetic is not as fast as the other system. So for making sure that data is valuable, we are talking about the high throughput data collection, so we can kind of rely on all the data that we gathered during these experiments, we needed to compare this with the isothermal hold. So for that, on the left, you will see the results of polypropylene in toluene. For the blue color, the triangles would be the data during the ramp, and the square would be the data during the isothermal. So we compared the first cycle at 25 degrees C and second cycle with the isothermal hold that we had for 1 hour at the end of the experiment. So as you can see, this data is matching perfectly, meaning that as we observed, the kinetic is fast enough and the data is reproducible, so we can rely on even extracting all the data during the ramp, because this gives us information, and it has a lot of information from 10 degrees C to 60 degrees C that we can use. Something that has not been done before, because all the data was just collected at one temperature with some instruments, and we didn't have this knowledge on a variety of or range of the temperature. On the right, again, you will see the polyethylene glycol in toluene, and we compare the first cycle and second cycles again with the isothermal hold. What we observe here is that the first cycle is not matching the changes during the second cycle and isothermal hold. That is because the polymer are, as I mentioned, being a large molecule and they are commercially bought, they store a little bit of thermal history. So when we are looking at a high throughput data collection, we want to make sure that this data is reproducible. That's why we kept it not only for 1 cycle, but for 2 cycles to match and look for reproducibility of the data. For that reason specifically, we looked at or collected all the data for high throughput experimentation during the second cycle for all these cases and during the isothermal hold. So these results shows that the first cycle is not matching. So we have to be mindful of what is the kinetics, what type of material we are working with. But the second cycle, since it's matching, is reliable data for further collection and faster data collection. So reliable data generation requires validation of RAM drive transmission against the isothermal hold, since we know that slow polymer kinetics can produce some non-equilibrium data. So now that we talked about how we standardize the method, we standardize our method to 900 RPM, going through 2 cycles of heating and cooling, and heating and cooling ramp rate were kept at 0.5 degrees C per minute. Let's look at some of the use cases, how we use this data that we collected in a high throughput manner, and how this data is useful. One of the use cases is specifically in this material class and in the polymers, because what to test, right? We have a lot of variety of the materials and variety of the solvents. How we can use a minimum data experimentation, but have better understanding a large space of the material, this material class. So I showed so far that how we developed a data collection method. Then I will show how we collect and process the data to generate a data set, and how we select and train the model, and how we evaluate the model on this polymer solution, how we can translate this transmission percent to a classification and evaluate the model performance even further. So after we standardize our method, we start collecting the data. These data were collected across 30 different polymers with 48 solvents. This work has been collaboration between the Professor Bredman lab and Professor Ramsar group during my PhD. So we looked at different solvent systems, from polar protic, and non-polar system, kind of equilibrium distribution between the polarity of the solvents. But this heat map is showing you how the data will be collected and what are some of the concentration of this material in our data sets. For most part, for faster data collection, we selected 15 milligram per milliliter. The reason for that is that this is not very dilute system, and more industrial processes are more interested in a little bit higher concentration, but not too high, because in the polymer solutions, the too high will come with some kinetic complication as well. When we are looking at this data in general, so the output of the crystal 16, if you remember, is the transmissivity, right? So we have the transmission percent. And if you look at the distribution of the transmission percent across all this data that has been collected, more than 900 cases of data has been collected, most of the data are in this region. We have 100% transmissivity, or biased towards the other end, which is 0%, meaning that either the polymer stayed soluble the whole time of the 2 cycles or stayed insoluble for the whole time. And we have a little bit of scar data between this partial solubility region. So as these images also are corresponding to this 100% and 0%, there are other challenges also involved. Another challenge which is inherent in polymer's material itself is that the noise in the material. So as we see here on these results, there are a lot of fluctuation as the polymer goes start precipitating. How we can find a signal to noise ratio, because we are talking about the machine learning, right? The accuracy of the machine learning, it depends on the accuracy of the data that you're providing to it. So we wanted to increase the signal to noise ratio for the model to learn more effectively. We used Zavodsky-Gloy filter in this case. We filtered data every 2 minutes, 3 minutes to get the signal, but avoid a lot of fluctuation in between. The reason for that is that Crystal 16 provides a very data-rich system. Every second you have a data points of the raw data. Going through this raw data of more than 60,000 data points for the same experiments, we didn't lose any kinetic insights, but we filtered the data in a way to increase the signal to noise ratio. Also, we removed any experiments with very large uncertainties, more than 8%, due to any reason that might happen. Solvent evaporation sometimes happen in by not closing the cap fully, or the material got stuck to the wire and things like that. So the standard deviation was also comes with some part of the experimentation. Following this method, we then wanted to tell the model what it's dealing with, right? We have the polymers and we have the solvents. How we teach the machine learning model that what is learning and what are the material that it's working with. So for the polymer, we used one-hot encoding, meaning that the model knows if the polymer exists or not in the solution. We were at the border of 30 polymers has been tested. It was not a Gaussian distribution between a large class of different functional groups. So we used n-hot encoding to just ensure that the model knows if the polymer is present in that solution or not. But for the solvent, the model is chemically aware of the solvent that it's dealing with. We were testing 48 solvents at the time that this study was done. So for that, we tested different fingerprinting methods to tell the model, based on the chemical structure of the solvent or smileys of the solvent, what are some of the characteristics that we can extract from the repository that is available, including the RT-kit. So as you see in this plot, there is no much difference between the Hansen solubility parameters, which is familiar for everybody, or Cortani, which is some chemical and physical properties, to Morgan, which is based on the chemical structure of the polymer. So mean absolute error is almost the same for these three, and the one-hot coding has a little bit of higher error. So we picked Morgan fingerprinting because we thought that it gives more information on the chemical structure of the solvents to the system. I don't share a lot of details in the machine learning to keep the story going and flowing, but if you're happy to discuss this, I'm happy to have another call or answer some of the questions. Then after we set the fingerprinting system, we went and tested different machine learning models from random forest, neural network, and XGBoost. And in comparing these three different machine learning models, XGBoost has a lower mean absolute error, meaning that the prediction is more matching what it is in the reality of the experimental data. After that, we built our production model which has the RMSE, root mean absolute error, of 6%, meaning that the model can predict the transmissivity of a polymer solution within the error of 6%. And the R2 square is 0.98, close to 1, indicating that it's not underfeed. And then for making sure that this is accurate for even unseen polymer and solvent cases. So we tested Li1, we did the test of Li1 out analysis for the model performance, meaning that we tested the polymer and solvent cases where the model has not have that in its repository, or it's not trained on this specific polymer and solvent system. When the concentration is 0, as you see here, the R2 square is 0.63, but as we increase the concentration of the same material to the model, then the accuracy also improves to 0.88 for only 2 concentration. This shows that how important is some of these parameters, like concentration, temperature, in training a machine learning model when we are talking about a phenomenon. So if you remember, I showed a slide on how the data was biased towards two end of 0 and 100%. And we had little bit data between the partial solubility cases, between 10 to 85. What we tested later is that we wanted to know if we increase the data points, we can increase the improvement of the model. And this was what we observed. So this is normalized confusion metrics. What we are looking for here is that we want these diagonal values to be close to 1, meaning that the two labels are predicted the same. So the prediction is accurate based on the true labels or the experimental data that has been collected. So these values we are expecting to be close to 1. If we look at the partial, which is in the middle, we see that with original data set, we have 0.90. And if you are adding more data within this range, we can improve the accuracy to 0.98. So we intentionally went back and ran some experiments with partial solubility behavior. So kind of like active learning, but not in a way that it's active learning. It all went with us, but this would be the future of active learning. Basically, the machine learning model learns from the data and designs some experiments to be run again and improve the data accuracy as we go. But if you look at testing this model prediction for the unseen classes, these are two examples, and we validated further our experimentation. So the true value, meaning that the blue one that we validated through experimentation for this pyopsin THF for 15 milligram per milliliter is that it's 100%, and the predicted value is 90%. So it shows that it's not 100% accurate. As you remember, we had the 6% RMSE, but it still is the same trend and value, or for the examples on the other polymer. And if you look at how does it look like, it's within the region of what we expected or what we classified at the start. Now that I shared this use case, let's a little bit talk about, was it really necessary to build the data set? Couldn't we go back and use the data from the literature, or use the data that, or choose a method that it's more practical and fast? One of the methods in polymer solution screening is the visual inspection that we also did for the same polymer system for some time before we get to run the experiments on Crystal 16. So for visual inspection aids with classification, right? So if I ask you, if we were in the room and I would ask you, how would you label these polymer solutions? How would you label as it's soluble, insoluble, or partially soluble? We will get to the point that we are biased to how do we classify these solutions, right? Even if I give you a definition. So this shows that these techniques, although it's very practical, right? We can just run it, it's fast, there is no expense or anything, and we can get the results out of pretty quickly. But this is also biased from user to user. What we validated is that we had the same data from the visual inspection with what we had from the Crystal 16, used the same polymer and solvent solution almost. We tried to match it up, the same number of data points, and the same machine learning and fingerprinting methods, and classified them as soluble, insoluble, and partially soluble, even for Crystal 16 data. So we classified those based on the cutoffs that I introduced. And then what we observed is that the turbidity data offers sharper class distinction than we are talking about underrepresented cases like partial solubility. On the left, we have the normalized confusion metrics for the visual data, and on the right, we have for turbidity data. Again, we want this diagonal number to be close to 1. And as you can see here, the partial solubility is very low value in compared to what we have here on using the Crystal 16. So we had a little bit sharper distinction between these two methods, kind of like, again, emphasizing that more precise method can have better data and more reliable prediction models. So to conclude this part of the talk, on how do we generate a reliable polymer solubility screening process, what is a comprehensive data set? I talked about the standardizing experimental methods for polymer solubility measurements using Crystal 16. We compared these results with visual inspection, and we also showed how the prediction model would use the Crystal 16 data for more meaningful prediction on the transmissivity. So what we can conclude is that the standardized data collection produced very well-controlled, well-detailed, and reproducible data for this purpose. A reliable production model for polymer solubility is possible with a data-rich data collection, because as you saw, a lot of times we have inherent noise in the data. And what to run, right? There are a lot of infinite number of polymer solvent solution that we cannot run all of them, but at least we can start and collect the data on some of them and expand from what we learned to a broader polymer solvent system. You also showed that while visual inspection remains practical, it still has some bias towards the measurement. And when we are thinking about the prediction model, the method is very important, and what it has been reported is very important. So not having all the data or having the data that is biased, it makes the prediction a little bit not reliable. So now let's dive into the second part. How can polymer solvent data guide the co-solvent screening? This is the chemical and physical properties of the polymer which is affecting the solubility, right? From functional groups, polarity, to molecular weight, melting point, crystallinity, and density of the polymer. And if I add two solvents to this, the complexity increases so much, not even between the polymer and solvent A or solvent B, but also with the solvent itself, right? So at the start, when we were thinking about, what would be the next step from here, from a binary polymer solvent system? Or for the goal would be the predicting of the solubility of the polymers in co-solvent system. What is the next step? The first step that it's easy to think of is that, okay, we can collect data on the co-solvent system using the same method that we used and use that as a training data. The challenge is that what type of experiments? It's going to be very time consuming, very labor intensive, and we cannot run all the polymer in different co-solvent system, right? How many to run? So how these insights on the binary system can help us to design this process. The second approach would be, okay, using some sort of weight percent as we have in pharma, right? What is the volume percent or weight percent of the solvent A compared to solvent B, and find some linear combination of these to relate it to the transmissivity that we observed. The challenge is that different behavior of the solvents in co-solvent system, right? And the possibility of the hydrogen bonding. We cannot this is not an ideal case. It's very much an ideal, non-ideal situation, and how we can address that non-ideality. The third, thinking about the predicting model, is that, okay, now we have, not only we have one solvent with the same chemical structure that we can use Morgan fingerprints, can we mix the two solvents together on the chemical structure and have them as one unique solvents with different kind of combination of the atomic structure, right? The challenge is it is better alternativeness compared to the other one, but also it leads to inaccuracies when the structures are very similar to each other. So from all these different methods, we wanted to optimize the technique to enhance the solubility in the co-solvent system, that is the target environment. What we did next, if we stepped back and looked at what governs the polymer solubility in co-solvent system, what are some of the definition or something that we learned from the literature that we can apply it right now. We have a very good literature or very depth knowledge on the Hansen parameters, which offers 3 different variables on the dispersion, polarity, and hydrogen bonding. We know now, based on the literature, that dielectric constant is another parameter that's affecting the co-solvent system. We also know the Flory-Huggins interaction parameters in the solvent system. It's very important when this polymer and solvent has the interaction parameter below 0.5, it means that it's soluble, and if it's above that, it's insoluble. But the challenge is that these are hard work. We cannot experimentally get this interaction parameter. It is almost impossible for what to do. It's very time-consuming or expensive computationally to simulate these results. And the other challenge is that there is preferential polymer and solvent interaction that emerge in the mixture. Solvent properties do not always match up linearly, and a small composition changes in the material can change the whole story. So can models that trained in the single solvent system predict these emergent behaviors? So we needed to go back and run some validation experiments. So we had some single data from the theory on the single solvents, from the Flory-Huggins, Hansen solubility, Hildebrand. We have some theories from the co-solvent system. We also have data-driven approaches between the binary polymer and solvent system. And we have something that we also learned from the literature on the co-solvent system. Can we combine everything together for a physically informed machine learning model? So we are not only collecting the data, but we are bringing a theory for more complex system to learn from it. So the goal was designing a physically informed machine learning model that can facilitate the prediction of the co-solvent system. Then we started preliminary experiments. We looked at the effect of the Hansen distance in the co-solvent system. We have one polymer, solvent A and solvent B. The Hansen distance is different based on different parameters. So we looked at the Hansen distance between polymer and solvent A and solvent B. We wanted to understand the polarity of the solvents and effect of the polarity on the phase separation of the polymer and effect on the transmissivity results in the co-solvent system. So we looked at that. We also wanted to understand and test the mixture of polymer in a co-solvent system. So what ratio to run, right? This initial screening was performed at a 50-50 solvent ratio because this composition maximizes the influence of the both solvents at the same time. As the most interaction-rich composition, it provides the highest likelihood of revealing some of these emergent phenomena in the co-solvent system, such as co-solvency, co-non-solvency, or other phenomena that it would be happen. It also give us a baseline that if this is happening, can we run the other ratios? So if you remember, we have the data on the binary solvents. So we have if it's plot, we have one solvent versus the other, and we are running right now 50-50 ratio. And from there, we are planning to expand to 25%, 75%, and vice versa to get more knowledge if the case is very interesting. So I started looking at the DOE strategy for selecting the co-solvent system. What I've shown so far is that some of the data are biased towards two ends, right? Either the transmissivity is above 85%, meaning that the polymer in solvent A and solvent B both are dissoluble. Does this mixture remain soluble for the co-solvent system of 50-50 ratio? Is it a monotonic behavior or co-non-solvency happening? Because the polymer is solvent in both of them based on the transmissivity. Is it dropping in transmissivity after we mix the 50-50 ratio? These are the areas that we thought that would be the most learning out of it. So we started the DOE design from these cases. The case 2 would be the condition where one of the polymer is soluble in the solvent A and it's insoluble in solvent B. Which solvent dominates? Is it the rule of mixture? Is it the volume percent is important in 50-50 ratio? We expect that if it's linear, the combination, so it fits between the two transmissivity. The case 3 would be the cases when the transmissivity, both of them is below 10% or we are in insoluble region. Can mixing improve the solubility? Is it the possibility of the co-solvency happening here? And we also had different behaviors, UCST and LCST, and we compared those cases with the cases that we had fully soluble condition. Does solvent B shift the UCST behavior? Does any of this are going through preferential kind of solubility behavior? So these are the areas that we wanted to take a look. We ran 37 experiments, and out of these 37 experiments, we defined some of the conditions that we expected to see. The first is the co-solvency, right? When both solvents are below 10%, does that increase the transmissivity to a higher level? Does this 50-50 ratio of the solvents help with co-solvency? Out of the 37 experiments, we have not witnessed any co-solvency happening yet. Out of these experiments, 16% exhibit the co-non-solvency, as this is example of polyvinyl formol, xylene, and chloroform examples. So we had this unique behavior of both of the polymer be soluble in both of these solvents, xylene and chloroform, in 1 milliliter of each, and then we mixed 50-50, and we saw a non-solvency happening, meaning that the transmissivity dropped to a lower value. 13% of these experiments exhibit the composition-dependent mixing, meaning that the solubility changes smoothly between the solvent A and B. Sorry, this label is not matching what we were talking about, but this is more composition-dependent mixing. As you can see here, one of the solvents is on the top, the other exhibit UCST behavior, and the co-solvent system is between these two, kind of linearly is matching. 30% exhibit the preferential solvation, meaning that the polymer is more matching towards the behavior of one of the solvents and mimic that. So then we wanted to go back and see if the Hansen distance is important here, if the polarity is something that is dictating this behavior. These are all study in progress. So I cannot, I don't have anything more to share on the conclusion of if any of these parameters are ruling this behavior. This is more thinking about the DOA design of how we can think from the binary system to a co-solvent system. The data is coming up, and this information, you can find it online in future from Bukwala and Bredner Lab. But another case studies that we also looked at is the composition-independent behavior. 30% of such behavior is that there is no change in transmission whatsoever. It stays at 100% or 0% throughout the experiments. So this shows at least 5 different ways that we thought that it might happen, and it happened with this experimental design system. It's still more to come, but this experiment has been done as a preliminary kind of like a screening to see what would happen and how we can translate that to the transmissivity, how the transmissivity would change based on the knowledge that we have or the parameters that we are talking about. So to conclude this part of the talk, towards more systematic co-solvent screenings, we talked about different approaches to think about a polymer and co-solvent system, how we are using a polymer solvent binary data to design a DOE for a ternary system, and how the physically informed model is necessary to capture the complexity of the system. The primary goal was not having, at this point, is not having a predictive co-solvent model, but this is a future that the group is moving into, but more like a systematic experimental framework based on what we built on the binary system. And this would be very valuable because in a lot of cases, we are not only work with the pure solvents. We want the co-solvent system for increasing the yield, for increasing the specific behavior that we are looking for. And again, going back to decreasing the solvent usage and having or designing a process, dissolution and precipitation process that matches what we want to accomplish. So with that, I would like to thank my friends at Bredman Group, Professor Bredman specifically for helping me throughout my PhD and postdoc, Professor Bukala as well for having me during the postdoc, and a lot of collaborators, Professor Ramsart Group, Professor Bukala Group, and Jacob and Joseph for contributing to a lot of machine learning in this project. As when I started, I was not computation savvy, but I had a huge help to do a lot of machine learning as well, to have a predictive models. So with that, I would like to thank you all for joining the webinar today. And we are in an hour, so I don't want to keep this webinar longer than what it be expected. I would be happy to answer any questions if you have. And get back to you later to answer some of the questions. Thank you so much for joining us. Please look for the future webinar offered by the TechnoBiz group. More is to come and more exciting research. Thank you all for being here today. Have a good day.